Okay, so image forgery detection approaches, first is an active approach, second is a passive approach. In active approach, you have seen digital watermarking and signature is detected, whereas in passive forgery detection, we have independent forgery, whereas dependent forgery. So in independent forgery, image retouching, and in dependent forgery, we have image splicing and copy move. You have earlier seen these approaches. Let's understand the forgery detection approaches. Active approach for detecting forgery involve pre-processing the image and embedded cipher key, which is used to authenticate the received image. Example is given as digital watermarking and signature. Whereas in passive approach does not require image pre-processing, it relies on identifying irregular statistical characteristics or pixel intensities resulting from alterations to the original image. The goal is to identify the grown tempered images, the absence of a need for a prior picture for the information, and make this technique preferable over the active approach. So the type of image forgery, first is image retouching, second is copy move, and third one is image splicing. I have already explained you first. Retouching means you have to modify the properties of an image, then it is called as a retouching. Whereas copy move means if you have one image, you can crop or you can copy the one portion of that image and paste in the same image. So that is called as a copy move. Whereas in splicing, you have two different images, you have to combine those two different images and make the third image. That is image splicing. So this is the simple example of copy move forgery. Here you can see there are two images. On the left hand side, we have original image, whereas on the right hand side we have copied some portion of one image and pasted into the same image, and we created this type of forgery which is called a copy move forgery. And right here you can see we have three images. Third image is created with a combination of first and second one. So we combine two images and make the third image, that is called a splicing. So let's come to our topic. Our topic is video forgery. And in this video forgery, we have a special forgery that is called intra-frame, and second one is a temporal forgery which is called interframe. So this intra-frame, in this intra-frame we have three type of forgery. One is copy move, second one is splicing, and third one is upscale crop. Whereas in the intra-frame or interframe, we have frame insertion, frame deletion, frame duplication, and frame shuffling. So these are different type of video forgery you can see in the videos which are coming nowadays. So this spatial tampering involve altering the visual element of a video frame along the x and y axis, known as spatial tampering. And spatial tampering can occur by modifying adjacent pixels, bits within a video sequence or a simple frame. And it can be performed at various levels, including pixel, block, or short sense level. The technique falling under the category of manipulation include crop and replace or morphing object additions and deletion. Whereas temporal tampering involves manipulating the manipulating the sequence of a frame or a video in a video. This form of editing primarily uh, impact the way of devices which record the temporal sequence of visual data over time, typically Tampering occurs at a frame level and involve adding, removing, and shuffling frames. Then this is spatio-temporal tampering, combines spatial and temporal tampering mentioned as above. And this manipulation involves altering both the time, sequence, and visual data. It modify both uh, the frame sequences and the visual content within the video frames. So let's see the block diagram of this traditional forgery detection technique. What we have uh, we can see right here. We will take the input image, then we will perform some pre-processing. So what do you mean by pre-processing? So we are using a deep convolution neural network right here, and you know very well that convolution neural network work on similar images, and the size of the images should be same, uh, and then it will work, otherwise it will create errors. So what we have to do right here, we have to resize our data, uh, and for deep learning we need large amount of data. So I will show you for this particular experiment. We can perform this particular video forgery detection on a large data set also, because when we take 1 minute video and let's suppose the resolution and the frame size of a camera which captured the video 60 frame per second. So in 1 second 60 frame, and you can calculate how much frames are there for 1 minute. So if you take 1 hour video, then how much data is there to analyze. So this type of problem cannot be solved on a simple machine. You need high end GPU for processing videos. uh, so this is the disadvantage. Who are working on video forensics, they need high end systems. So they cannot perform the operations on simple machines, because the processing power we require to perform this forensic is very much large in this case. So after pre-processing, we have to perform some feature extraction. So extraction means we have to extract some edges, some color portions, some sharpness over there. If there is an abrupt change in the image, how the image is there. So we have to find out such type of feature extraction. In deep learning, this process is automatic. Just we have to select the filters, and with the help of those filters we can automatically detect those edges, sharp portions, and the abrupt change in the intensity, as well as other deformation or formation of that particular image. Then after performing feature extraction, we have to apply some classifications. So classification means we have to use SVM classifier to classify what type of this image is. Either it is a forced one or not forced one. Then after that, we have to perform some post processing if you want to find out exact portion of that image where forgery is present. So this post processing is to be performed at that particular point. So in machine learning approach, there are three type of machine learning approaches. One is supervised learning, second is this unsupervised learning, third one is reinforcement learning. So in supervised learning, we have labels as well as ground truth images. We can say label is a ground truth images. So whatever we have original image, and we have the ground truth image, the label of that particular original image is also present in supervised learning. So first we train the model with the original image and showing the image that this portion is forged and this portion is not forged, and accordingly the machine learning model detect and it learn from the training part. And generally we divide our data into this 70/30 or and 80/20 ratio. So this proportion we have taken for our experiments, you will see in the lab sessions. In unsupervised learning, we don't know the data, the labels. We have the original image which we have captured or which we have received from unknown sources, and we don't know which portion is forced. So this unsupervised learning, we use autoencoder for this unsupervised learning, which divide the complete picture into different small portion of pixels, and then we perform the clustering and those things, and to identify the patterns in between those images, and we will detect which portion is uh, which portion is an outlier, and then we detect that portion is a forced one or not. Then reinforcement learning, this is a reward and penalty based system. Generally, when the agent perform the accurate result, we give the reward to that particular agent. If agent is performing the wrong thing, then we penalize that particular agent. So this is called reinforcement learning. So machine learning, generally these three basic supervised, unsupervised learning, and reinforcement learnings are used. So you can see the definition right here in supervised learning. It is called supervised learning if we have input data and its output data. Both input as well as output is available with us. So we can call it as supervised learning. Most image forgery detection techniques where a ground truth image is available for training and testing are based on supervised method. Thus, finding forgery turns out to be classification problem. So in this, we can classify the type of image portion. That portion is authentic or that portion is forged. In unsupervised learning, when a real-time input is given to the unsupervised model, it automatically find the patterns. You can see right here, it divide the image into different small pixel blocks, and then it find the patterns in between that pixels, and based on that pattern, it create the clusters. So it cannot add labels to the collection, like it cannot say this is a group of forced, uh, not forced image, but it will separate all responded images from the data set. Reinforcement learning works on reward and penalty. As I have told, uh, uh, this particular reinforcement technique is used for reward and penalty. The agent automatically enumerate the solutions, and computer computes the bonus and penalty. The agent interact with the environment and it take actions. If the move turns out to be incorrect, it is penalized. So if the move turns out to be correct, it is rewarded. The cycle goes on and until it ultimately turns the environment properly. So this is the three basic machine learning techniques. So in artificial intelligence, generally you can see from this particular image, this artificial intelligence is a wider area, whereas machine learning is the sub part of this artificial intelligence, and deep learning is sub part of this machine learning. So it come under all come under this artificial intelligence. Now come to the next model, which is taken right here for image forgery detection. So this is our paper. In this paper, what we have done, we have performed machine learning task to detect the forged portion on COMFD dataset. And COMFD is a dataset which is freely available on internet, and it is the open source. You can also download this particular dataset, and you can see what we have done in this particular machine learning algorithm. We have taken the data set, then we have performed the pre-processing steps, then we have used the segmentation map and color illumination, then we have performed adaptive over segmentation using this slice O algorithm, then we have performed soft and shift feature extraction technique to extract the feature, then we perform the correlation which map the feature map, and then feature point labeling is to be performed using SPM, and it classify which portion of the image is authentic and which portion of image is forged one. So you can see from these images, this first image is a forged image, and in the second image, what we have done, we are performing right here uh, color illumination as well as the mapping for segmentation, and then this adaptive over segmentation is performed. With the help of this particular result is generated, and then we are using this feature extraction surf and shift method. You can see these features are matched, and these shift and surf will detect a particular portion. And lastly, this localization, SBM will match the features, and it will localize these portions, and you can see the result right here. So deep learning, when it comes to deep learning, feature extraction is automatic. Deep learning is a technique to implement machine learnings, and it is the subfield of this machine learning. So right here, uh, in this particular algorithm, what we have done, we have used this hybrid algorithm. So this emphasis is given to the forgery classification and localization portion. First is the pre-processing, then we generate the training and validation data set, then we perform the CNN operation. Third point, fourth is we have performed different steps on this deep convolution neural network. Then in the fifth step, we are using this fully connected layer. And then sixth, we are using the training part. Seventh, we have, after training, we have to validate our model is going to uh, perform in a better manner, like there is overfitting or underfitting. So if there is overfitting and underfitting, then again we have to change, we have to increase the data size, and then we have to perform the validation step again. And in the eighth step, deep convolution neural network classifier is used. And in ninth, we have extracted the features. And then in 10th, we localized the portion of the image forgery. So in the figure 11, you can see these are the results which we have achieved uh, over a different epochs. So you can see in the first epoch, our accuracy, time elapsed, as well as iteration. So you can see this gray line, accuracy. So first point is right here. In the epoch 1, 50 iteration is to be performed, and then the accuracies for this is about 50%. Okay, and again, after this, first to 50, you can say 85, epoch 100, this 100%. After this, saturation is there, no change after 100%. So you can close this particular training push training at epoch number 100. So this is the wastage of resources right here. So for the experiment purpose, we have seen further this is increasing or not. So let's see how this deep learning is working. Right here, first we have taken the input image. So these images are applied to the convolution neural network, and this convolution neural network perform different operations. First, it will take the uh, take a kernel. So what is that kernel? Kernel is a filter. So you have seen in the yesterday session that 64 uh, filters are taken, and then the filter size is increased. Initially, you have seen the image size is taken as a input to the filter. You have seen 52 cross 52 filters, then 64, then 64 multiply by 2, that type of filter you have taken, then again you multiply by 2. So the filters must be multiple of 2. Initially you start with the lower portion, like you take filter size of 16, then you increase the filter size to 32, then you increase the filter size to 64, then increase the filter size to 128. So in this manner you can increase the filter. So a filter is nothing but a portion of a small portion of this particular pixel that is to be multiplied on the image, and we are performing convolution on that particular patch, whatever the size of that particular patch is there. So let's say you are taking a kernel size of 3 cross 3. So first is 3 cross 3 kernel is there. So you multiply each pixel with the image pixel, and then you take a stride of 1 or 2. It's up to the programmer. He can take multiple stride also. So the kernel is moving from one portion to the another in a horizontal manner, and then we are using padding at a last, because this padding, after convolution, the size of the image is reducing, and after reducing the size, we have to match the image with the another image. We have to pad 0 to the boundaries of that particular image. So in a yesterday session, you have seen first convolution is applied, then you apply stride, then you applied the this padding, then you have seen that pooling operation is there, max pooling. There are three type of pooling. First is a max pooling, second one is a average pooling, and the third one is a mean pooling. So generally we take max pooling, because if the pixel size is maximum, that is the maximum information is there. If you take mean pooling, that means there is less information. If the pixel value is less than, it is not showing in a good result. I have observed when we perform different operation over there. Then this pooling layers are there, and then after pooling we are using this flattening layer, and after flattening we are using fully connected layer, and then we are finding right here some classifier, which with the help of a classifier we can find out the probability for these neurons. So let's suppose that we have 1 2 3 4 5 6 7 8 these neurons are there, and we have only two output classes. So each neuron is each value of these fully connected is multiplied with the each neuron, and it will be again multiplied by these two values, and whatever the value which give the higher result, that is considered as a forced or not forced value. So either it is one, or it is a zero. So there are a relu operation is there, leaky relu is there, different soft this particular activation functions you have used. So let's say the proposed technique which we have used right here. So in this proposed technique, we have used 25 layers of deep convolution neural network. So what do you mean by 25 layers? 25 layer means we have taken 25 convolution layers. So these are the two-dimensional convolution neural layers, and in which the input size of the images are taken as 114 cross 114 cross 3. So cross 3 means it is a color image. It has three channel, red, green, and blue. So that's why this 3 is the dimension of that particular depth of that particular image. So three dimension. And 114 is the length, 114 is the breadth, and three channels are there. 2D convolution layers are placed on a layer 2, 5, 8, 11, and 14, and the layer number 17. And in between convolution, we are using a ReLU layer that is placed at layer number 3, 5, 9, 12, 15, and 18, which calculate the node output in a neural network. The 2D max pooling is placed at layer number 4, 6, 10, 13, 16, and 19. And four layers, that is layer number 20, 21, 22, 23, they are fully connected layers in the network, and individually node is connected to the every single node in that neural network. So that's why we can call them as a fully connected layers. So at last, on layer number 25, we use softmax activation function, which is used as an output to classify whether that image is authentic or forced. So Optimizer we have used in this particular training part, and it employed during the training phase as it required low memory and outperform large data sets. The initial learning rate we have used 0.001. So why we have taken this initial learning rate very small? Because if you take a large learning rate, then local minima will be crossed, and it will stuck somewhere else. It will predict accurately for few images, but later if you give uh, unknown image, it will not work properly. So with the small learning rate, your model is going to be fit very accurately. With L2, regularization factor is 0.004. It is also very small because regularization is to be performed on each and every node. So that's why it is also taken as 0.004. So learning drop rate factor is zero point 0.5. Drop rate factor means those neurons which are giving the value 0. That means they have no information. That's why we are using 50% of such type of neurons which are giving 0 output. We are going to drop out those neurons, and the learn rate period is 10. Learn rate period is 10 means how accurately, how fastly it is going to learn the model. So we have taken it 10, and additionally the data is shuffled over each epoch. So after performing first pass, the data is going to be shuffled so that our training is more accurate. So we are using a valid train data set to train the model, whereas valid data to validate the model. And the three is the validation frequency, and we provide 1000 maximum epoch. This is for the training only. What we have seen earlier in the previous slides, at 100 epoch, our model is saturated. After that, no use of performing the training, but we have taken 1000 epochs. So it is in between, we cannot stop that model, because after the completion of the training, then the model is going to be saved in our H5, this particular model. Okay, so .h5 file. So that's why we have taken this, and with 100 mini batch size we have taken. So if you have a GPU, then you can take that much large batch size. If we have a GPU in our lab, that's why we have taken 100 mini batch size, because those GPU can handle this type of batch size. But if you have a laptop, so more than 64 or more than uh, 32 batch size you cannot take, because your CPU is going to be heat up, and it is not going to perform the task. So that this is one major disadvantage for large data set to be processed on GPU only. And Google Colab is also not working at such type of large data set, because uh, it will break connections in between, and your whole training part is wasted. So we have to perform this task on GPUs. Verbose is used to display the training process. So verbose means whenever you are performing the training part, the window will show the training process. So how much accuracy is there, how much validation loss is there, how much epochs are going to complete, how much iterations are going to complete, how much frequency is there, how much resources are to be utilized. So whole process is to be shown with the help of this purpose. So let's see the results and comparisons. Here you can see after 100 epoch, our model is predicting approximately 95 to 97, and at 200 epoch it reaches up to 99% of accuracy for the training set. Whereas for the validation set, for 200 epoch it is showing approximately 88 or 89%. So we have trained this model for 1000 epoch. So after let's go 500 epoch, it is going to saturate. So this is the loss which we have achieved at different epochs. So you can see at epoch number 20 to 200, it is reducing slightly. So that's why the training epoch are taken 1000. So it is reducing slowly, slowly. So these are the references which we have used to create this presentation. Uh, if you have any question right now, you can ask the question. If there is no question, then we will start the practical session. So you can ask question if you have right now. Yes. If you have any question, you can ask right now.
No, sir, no
Yes.
question from my side.
Okay. So you want to see the practical session?
Yes, sir.
Okay. I will take a 5-minute break.